on Mars, it's a bit more flexible because we don't have that pesky vegetation.
You're listening to The Cosmic Cast.
Hello everyone, and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System Group at Manchester University. You're here with me, Ricky Bahir. We also have Dr. John Pernott-Fisher.
Hello.
Tom Harvey.
Hello.
Marissa Lowe.
Hello.
And today we have an amazing guest for you all. We have Dr. Frances Butcher.
Hello.
So Frances, you are currently at Sheffield University studying ice sheets, trying to reconstruct them from their past. And I was just wondering how you got to this position, essentially.
Yeah, so I'm currently a postdoc in Sheffield. I finished my PhD, about a year ago now. And my PhD was actually in planetary science, studying glaciers on the planet Mars. So I've sort of come back down to Earth for a few years. So I'm currently reconstructing the flow histories of Earth's past ice sheets. And that's both for important climate change science here on Earth, but also personally for me, in order to gain more experience of actually what glaciers do on Earth and what their imprints are, so that I can then go back to Mars and get a better insight into how glaciers have shaped the planet Mars. And to get into this, I started off as a geographer. So I did a geography degree at the University of Cambridge. And I sort of focused in on glaciers quite quickly. I love the glaciers. All of the physical things I gobbled up. And I pretty much, when I applied, I knew I wanted to do something about the geography of the planet. So my personal statement had me talking about Valles Marineris on Mars and things like that. And so I sort of knew that I wanted to apply it, but I wanted to get sort of the Earth background first. So I did geography, and then for my undergraduate dissertation in third year, I decided to apply glaciology to Mars. I found out that there are glaciers on Mars, which I didn't know at the beginning of my degree, so I was quite happy about that. And so I did a project, which I actually went to the Open University over summer, where there's a planetary science group, to do that research. And I ended up joining the Open University for a PhD thereafter, after I finished my undergraduate, doing glaciers on Mars. So I was very much looking at glacial landforms on Mars and also the glaciers themselves. And that really allowed me to sort of connect both with the Mars geomorphology literature, but also with Earth glacial landforms. So I did a lot of overlap and comparison work in my PhD. So now I'm back on Earth, sort of grounding myself back in that terrestrial stuff.
Yeah. I was going to say, it's really cool that you can sort of jump between planets like that, but presumably all the fundamental principles are exactly the same. I suppose it's a bit more unusual to go from extraterrestrial to terrestrial. I guess normally it's the other way around. How have you found that going from Mars back to Earth?
I think it's really important. I don't think you should certainly never do Mars in isolation. I personally think you shouldn't do Earth in isolation either.
Yeah.
But I'm biased. And I think, so as I said, my first 3 years of my undergraduate were entirely Earth. So I did volcanology, biogeography, quaternary science, and glaciology mostly. And so I did sort of have that sort of theoretical background that I then could apply to Mars. I have found it really, I found it really interesting, having done my PhD focused on Mars, to jump back to Earth. Actually, I'm seeing Earth in a new light. I'm having all sorts of, like, I can't spend one day without jumping between planets and thinking, oh, I've seen that on Mars, and oh, I've seen that on Earth, and it's really good fun. And yeah, I have some good conversations with my sort of terrestrial colleagues as well, who get really excited about things I find on Mars.
You mentioned it's reconstructing past glaciers. How far back can you look at glaciers on Earth? Is it constrained by, because presumably a lot of the sediments and stuff you're looking at get eroded quite rapidly, or I don't know anything about sediment.
Yeah, if the glacier is producing meltwater, it quite quickly can destroy what was previously there, although things can get preserved. So I'm actually reconstructing the flow of the Scandinavian ice sheet currently, that covered so Norway, Finland, Sweden, and the south of the countries to the south of the Baltic Sea. And I'm primarily reconstructing its retreat, so how it flowed since 21,000 years ago, something like that.
So it's all since the last ice age, basically.
Yeah, sort of the death of the last ice age, as it were, as the ice sheet was retreating, and sort of working out how it flowed in that time, because that's quite important for understanding the sort of climatic implications and things like that.
So how do you do that? Does it involve like mostly field work, you know, looking at outcrops, or is it more looking at satellite images and say the more picture side of it?
So it's actually a big collaborative project. So there's postdocs and PhDs, there's modelers, there's geomorphologists, there's mappers and things like that. So my aspect is primarily using satellite images, satellite and aerial digital elevation models, so elevation models of the surface. So my Mars work was primarily using elevation models and images, high resolution images, but obviously on Earth you have vegetation which gets in the way, so you have to use laser elevation models of the surface derived from laser, i.e. LiDAR.
Can I just say that's such a Mars researcher way to look at vegetation, by the way.
I know, right?
Gets in the way. Always gets in the way.
I do still think that objectively, Earth is probably the best planet. It keeps us alive, which is quite handy.
Yeah.
But
makes things easier.
So I basically map the landforms produced by the flow of the ice sheet, and that can get really quite complicated because obviously the flow of the ice sheet has changed over time, and so you get sort of stacked imprints of ice flow. And then there are other people on our project, which is a European Union funded project, who are mapping meltwater landforms, so looking at how the meltwater drained across the underneath the ice sheet. And then there are people doing computer modeling of like how specific landforms form and what the sort of dynamics of those processes are. And actually something that's really interesting that's coming out of that is that sort of questions that we're asking about glacial landforms on Earth and Mars are sort of happening at the same time, because effectively we got the data at very similar times. So the really high resolution elevation data of Earth, we got at a similar time to when we got that for Mars. And so what I found during my PhD actually is that I was asking questions that were people working on Earth landforms were asking at exactly the same time. So I've made some really nice collaborations with them, and we're sort of pushing the frontiers together. So one of the things that I think Mars could be really interesting for understanding glaciers and ice sheets on Earth is that on Earth, you can, with models and things, you can change loads of parameters. Let's say you can change the thickness of ice, or you can change the temperature of the ice, or the temperature of the atmosphere, or things. Something that you can't change easily is gravity, and things like atmospheric pressure. What does atmospheric pressure and gravity do to the fundamental physics of glaciers? And so we're actually asking questions of Mars that will help us to understand how those really fundamental parameters affect the process on Earth. And even though maybe gravity doesn't vary that much across the Earth, it's still important to understand what these real fundamental physical constants are actually doing to the theory. So that's quite interesting.
So presumably on Mars then, do things just sort of spread out a bit more because of the lack of gravity, or? Oh,
if only if it was that simple. So one of the main landforms that I study is called an Esker, which is effectively, it's like sediment that's accumulated in a subglacial meltwater channel. So the meltwater effectively carves a tunnel underneath the ice, into the ice, not as a river channel necessarily, but actually as an upstanding tunnel. And that infills with sediment deposited by the meltwater flowing through it.
So these are these famous inverted channels of Mars.
Well, they are slightly different from inverted channels, because inverted channels are actually rivers, like subaerial rivers,
right?
Whereas Eskers are subglacial rivers. So they are slightly different things, even though the sort of process that forms them is a bit similar.
What causes a certain area of an ice sheet or glacier to start melting as opposed to another area of the ice sheet?
Well, there's all sorts of, it depends if you're talking about the surface or the bed. So the surface is primarily things like temperature, things like that. But the bed is a combination of things like pressure. You might have, so pressure, temperature, thickness of the ice. If you have any salt in the ground, then that can promote melting at sub-zero. And that's potentially something that's been quite important on Mars. So yeah, it depends. If you're looking subglacially, you can form subglacial meltwater even if the surface temperature is below zero, because the beds of ice sheets are generally warmer than their surfaces. And nice and comfy and blanketed.
So at what point so I don't know much about Mars's history in terms of glaciers and also water and all that. At what point in Mars's history was it glaciated?
So Mars is glaciated now. So it's got polar caps that are about 3 kilometers thick in parts at the thickest points. So that's sort of present day polar glaciation, similar in a way to Antarctica and Greenland. But it also has relict glaciers in its mid-latitudes, so similar latitudes to where the UK, Northern Europe and North America are, and also similarly in the Southern Hemisphere. And they're more like valley glaciers and crater glaciers, and they're very abundant. There are thousands of them, and they're actually covered in a blanket of dust and debris that protects them from the very thin atmosphere in the present day. So the atmosphere is so thin on Mars now that at the moment, under the current orbital configuration of Mars and its current climate, you couldn't accumulate ice there for long periods of time to make a glacier. But because they've been blanketed by dust over time, they're protected from ice loss. So they're still there, but they're covered in stuff. But you can still see how they flow, and it's sufficiently thin that you can sort of see the structure of the glaciers underneath, which is very pretty.
So I guess the point Marissa might have been thinking about is active glaciation in terms of moving glaciers then. So when do you think in the past glaciers were eroding the surface of Mars?
Ooh. Well, that's a multi-dimensional question, because glaciers tend to only really erode the surface if they melt. They can erode when they don't melt, when they're just cold, but that's another question. However, there is evidence from the surfaces of these glaciers that they have flowed. So whether that flow is entirely within the ice itself or including some amount of the ice sliding along a bed, which would generally cause erosion. But the fact that they have flow lines means that, yes, they probably flowed. And we can get from impact crater counting, so looking at the number and size of impact craters on their surfaces, we can look at an approximate age for the most recent resurfacing event. So the most recent period when perhaps flow eroded, when flow of the ice reset the impact cratering record. And since then, craters have accumulated. So we can get an approximate date for that. And it varies quite a lot, but in general, they're geologically young for Mars. So they tend to be, the very youngest are a couple of million years, and the oldest are up to 1 billion years. Oh. But in general, they're around a few 100 million years. Oh, wow. Which on Earth is ridiculously old, but on Mars, that's very recent in its geologic history, given that it's basically thought that its surface sort of went a bit dead after about 3 billion years ago. So things happening 100 million years ago is very recent.
Do you think that's just because of localized heating events allowing these things to move, or?
Their flow seems to have been pretty ubiquitous. So the accumulation of these glaciers is in Mars's mid-latitudes is thought to have been driven by changes in Mars's orbital obliquity, so how the planet tilts towards the sun. And so it's thought that when Mars was a bit more tilted than it is now, ice moved from the poles down to the mid-latitudes and accumulated, and that ice flowed. So they might not all have been flowing or even accumulating at the same time. That's probably an oversimplification. But currently our dating methods just aren't good enough to really distinguish between probably between spatial flow events and things like that. Yeah, so, but in general, they've flowed recently.
That's really, I guess, that must have some really important implications then for understanding habitat environments. If you've got water and glaciers that are sort of present and flowing, as it were, so early on or so recently, then that's got to, it must be really important for understanding these environments then. Yeah,
so subglacial environments are becoming really interesting biologically. So until quite recently, it was thought that subglacial environments were horrible and why would life ever want to live there? But actually, there are a lot of processes happening under glaciers that are really important, certainly on Earth, including crushing up of rock. So if you crush up the rock, you make lots of nice nutrients from the rock that microbes could use. You also have availability of water ice that can create liquid water. So that might not be massive flows of liquid water. That could just be like little lenses of water between ice crystals. But that's big enough for a microbe. The areas that I studied on Mars, which are very rare, there are 2 glaciers that have been identified so far that did have probably quite catastrophic liquid meltwater events that formed those landforms called Eskers that I spoke about before. So they're extremely rare events, but they're also usually quite high energy events, which probably you wouldn't want to be a microbe if that happened. You probably wouldn't want to be hit by the torrent of water that formed them. But that's not to say that elsewhere within that glacier there might have been liquid water environments that were much nicer for microbes. So yeah, it's got some really interesting astrobiological implications, the fact that there's ice there. And actually some recent work that I've been doing has actually shown that we might potentially be able to access the material from the beds of the glaciers without actually drilling down to their beds. So I mentioned the flow lines that you can see on the surfaces. Well, I've actually found a glacier on Mars that's actually been incised by what's called a gully, which is like an erosional landform where you have like an alcove eroded into a slope, and then you have some kind of transportation channel and a fan at the end where that material is being deposited. And it's actually eroded through a glacier, and it's cut through some of the flow lines that you can see. And what it actually shows is that it looks like material has been transported from the bed of the glacier internally up to the surface of the glacier. And this incision has exposed this structure that connects the surface of the glacier to the bed. And that's very common in glaciers on Earth. And they tend to transport material from the bed to the surface. And so potentially we might actually be able to access material that could have astrobiological interest from the surfaces of the glaciers rather than having to drill to their beds.
Yeah, that's amazing.
Which is pretty cool.
Yeah. Have all these sort of glacial regions been fairly well mapped now, or is there still a lot of Mars where simply the work hasn't been done to recognise where a lot of these features are? And
so there's some early, some quite good catalogues of where they are, but there's still a ton of work to be done. There's a ton of work to be done on glaciers on Earth, let alone glaciers on Mars. So yes, it's still very much an exploratory science. We're still discovering new things.
Yeah.
And I'd say there's plenty of space for lots of glaciologists to go to Mars.
Yeah, it probably has implications then for understanding the timescales of glaciations. I suppose the hundreds of million years could be pushed to even more recent ages then, the more we understand where these features are and what their sort of settings are.
Yeah, I mean, Mars's tilt, it's tilt towards the sun, it's obliquity, which is what drives these glaciations. It's changed on pretty rapid timescales, actually similar timescales to ice ages and interglacials, which are sort of non-ice ages on Earth. So the tilt sort of varies on a timescale of, I think, 120,000 years between what on Earth would be considered a glacial and an interglacial state. So actually, there's probably been quite a lot of mobilization on quite short timescales, even by Earth standards. So yeah, there's potential that there's been prolonged, but also multiple episodes of glaciation. And actually, a recent paper by a colleague in Aberystwyth called Adam Hepburn has found that there are very young glaciers sitting on top of very old glaciers. So glaciers have advanced over other glaciers, which is pretty cool. It's a really nice paper. yeah, so there's all sorts of weird stuff going on.
Yeah.
So what sort of data do you use to study these glaciers?
So whereas on Earth, I'm primarily using elevation data from LiDAR, which is laser altimetry. On Mars, it's a bit more flexible because we don't have that pesky vegetation. So we can use high resolution images. So I tend to use either the global coverage of 6-meter resolution images from the context camera, called CTX, or very high resolution images from the HiRise camera on the same orbiter, the Mars Reconnaissance Orbiter, which is 25 centimeter resolution, which is ridiculously good. It's I think those people get quite jealous.
Those HiRise images are amazing, aren't they? I think it'd be worth linking that in the description of this episode for people to have a browse, because they're incredible pictures. Yeah,
they're mind-boggling. That in some ways there's too much detail. You zoom in, you're like, whoa, there's too much going on here. And you can actually use them to make very high-resolution elevation models of Mars, so 1 meter resolution. So you can see incredible detail. So the elevation models of Earth that I'm currently working with tend to be about 2 meters resolution. So actually, the ones I work with for Mars are a bit better. I mean, they're not derived from laser; they're derived from what's called stereophotogrammetry. So there's potentially some difference there, but they're at least on a par with the Earth data.
Did you need high-rise images when you saw that gully then cutting through a glacier to see all those different layers that were there?
Yeah, so it was so I spotted it in CTX, so the 6-meter resolution. So I could see that there was a gully cutting the glacier, and I could see that there were flow lines cutting the glacier, and I could see the structures that I was talking about that connect the bed to the surface, but not in great detail. But there did happen to be high-rise coverage of it, and also enough high-rise to make an elevation model. And what that drew out was the detail of those structures, but also the fact that they have a really interesting color anomaly. So the internal structures that I think are probably debris rich have a different color signature to the rest of the glacier. So that in turn suggests there's either some difference in roughness or in composition, which would support the idea that they might be transporting stuff through them. So yeah, it was a kind of a mixture of data, but 3D and image data go into it.
And is this the well-known process then? Do people understand why this transportation would be occurring, or? It's
very common on Earth because, so this isn't actually peer-reviewed yet. I haven't actually submitted the paper, but it's going around some conferences and it's getting, I'm quite excited
because I'm going to publish it.
This is why you're asking about the data, right? So we're actually, so on Earth, the structures tend to occur at the sort of near the termini of the glaciers, and this is exactly where we see them on Mars, where we've identified these structures, and that's generally because towards the end of the sort of terminus of a glacier, the ice is slowing down, because basically the ice is getting thinner, so there's less drive behind it, basically. So as you get ice slowing down at the terminus, the ice behind it bunches up and sort of compresses, so that they very much look like compressional flow lines. And in the case that the glacier is wet at the bed, so in the case that it's got meltwater at the bed, you can create what are called thrusts. So some of the ice behind the terminus thrusts up over the terminal ice, and that transports bed material with it. More likely in this case, because it's Mars and it's very cold, and I don't see much other evidence for melting, it's more likely that the bed has been frozen and it's been some kind of folding process. And that's a bit more complex, but it can still transport debris to the surface. So you don't necessarily get a brittle failure in the ice like you might with a thrust.
On Mars, we'll see. Do we think that on Mars the glaciers were purely water? Because am I right in thinking some of the glacial polar caps are mostly CO2, and would that have been a factor in some of these mid-latitude glaciers?
So the polar caps, slightly different compositions. So the south has a perennial, so year-round covering of CO2 ice, but it is predominantly water ice underneath.
Okay.
And the North Polar Cap is mostly water ice. There is a CO2 cycle on Mars, so there's the atmosphere is primarily CO2, and it's cold enough for it to condense into frost in winter. So we have a ground penetrating radar, or 2 ground penetrating radars orbiting Mars, and the composition based on those radar observations of the mid-latitude glaciers is consistent with water ice.
Okay.
There hasn't yet been spectral evidence of it, but it does seem consistent with water ice, and climatically it would make sense. The climate model suggests it's water ice as well.
Yeah.
So yes, I think they're predominantly water ice, if not entirely.
Mm-hmm.
So if we take a step back to, you were observing these Eskers, that was a massive part of your PhD, was actually looking at the Eskers. So things that hint at flowing liquid water underneath an ice sheet or a glacier. Can you get an understanding of how much water was there, or a quantity of water, or time, how long the water would have to flow for, or anything like that from these Eskers?
It's very difficult.
Okay.
So what, in summary, in my PhD, what happened was I found one of the early Eskers to be identified in association with a mid-latitude Martian glacier. So it suggests that glacier had melted at some point in its history, which is very unusual. We don't think in general that many of the glaciers produce meltwater. So in general, Eskers are formed by high energy flows, so rapid drainage. But to be honest, we don't really know for certain how Eskers properly form on Earth. So there's still a lot of debate around whether they form in a single event that's some kind of flood from a subglacial lake or something, or whether they form gradually over time at an ice margin as the margin retreats. So you sort of get gradual accumulation of these ridges up glacier. In general, it's probably the case that some Eskers form by one mechanism and some form by another mechanism. But really, it's tricky because one of the main ways you can understand Eskers is by going and digging into them and looking at exposures of their sediments. And
you're not going to do that for Mars, then?
Oh, I've got my spade here waiting. I'm just waiting for my lift on the rocket.
When isolation's over, then you can head up. Yeah, that's fair enough.
Yeah. Oh, this isolation, it's put everything on hold. So that's something that I'm really working on trying to overcome. It's a problem that will probably forever affect us with our Mars research, is actually being able to look at the sedimentology of these things. But people are starting on Earth to connect the interior sediments of Eskers, so the things that really tell us about the flow events that formed them, with the sort of overall morphology of the ridges themselves, and sort of their geometries and what they look like and what their shapes are. And that's helping us to understand the linkages between what you might be able to see in remote sensing with what you might be able to see if you go and hit it with a hammer. And that is something that my PhD also tried to start looking at for Mars in particular, and I'm continuing to look at, which is, can you actually infer stuff about the flow process by just looking at the measurements and the geometries of the ridges and their morphologies? And I think there's promising signs that you can. So I've got some work going on that as well. So I've got my fingers in a lot of Mars pies and a lot of Earth pies at the moment, as you can probably tell by the way we're jumping around between Earth and Mars.
I was going to say, are there any other pies in the solar system that you'd like to get involved with?
Ooh, so I think Pluto's really cool. I think there's a really great team already working on that. So I'm not going to go and invade their space right now, but there's some really, really cool morphologies going on there, including like nitrogen glaciers and ice convection and water ice mountains. Like, it's the glaciologist paradise. So maybe we'll go back there one day and get some really high resolution images. That would be really cool.
Has there been much work done on looking at different compositions of glaciers and how that affects their flows and things like that?
Yeah, I think there was a paper recently actually on specifically on Pluto and
Okay,
how the
yeah.
composition affects it. There's also some research into how the flow of glaciers on Mars might be affected by their composition. So what the effect of debris concentration, gravity, salt concentration, things like that, how that might affect their flow. Because obviously if you have debris or impurities in ice, that can affect how the crystals flow past each other. It's all very complex science, and it's still in progress on Earth. So this is, again, this case of Earth and Mars kind of evolving our understanding at the same time.
I think you mentioned earlier that some of the work you're doing now links to understanding climate change. Is that with respect to just understanding climate history, or?
So the direct result of the mapping will be that we understand better how the ice sheet flowed over time, and we can link that to climate records from the past. However, the really key thing about this ice sheet reconstruction project is that basically if you tie the reconstruction of the flow from observed landforms to ice sheet modelling, you can effectively improve those ice sheet models to reproduce a landform record produced by a retreating ice sheet. So Antarctica and Greenland are currently retreating, but their landform record is still mostly obscured or yet to be created. So we don't have that tool for the present day ice sheets. So if we can get the models to reproduce the landforms being formed that were formed by past glaciers, and that those reconstructions make sense glaciologically, then we can improve those models to predict how the current ice sheets might respond to climate change, because it's all about improving the physics and the reconstructions of the models. So that's how it's going to tie into helping us to understand future ice sheet responses by looking back at the past. I hope that makes sense.
Yeah.
So who are all the different organisations involved with the project that you're working on then?
Well, there's lots of collaborators, but it's based here in Sheffield. We have collaborators in France, in Finland, people in Manchester working on it. It's quite a nebulous project. There's quite a lot of people involved. It's really exciting. It's bringing together lots of expertise in ice sheet modelling, mapping, geomorphology. There's also a dating component to the project, so ice sheet chronology and dating sediments. So watch this space. It'll be an exciting result when it all comes together, but there's a lot of hard work still to be done.
So a question that we ask all of our guests is if you could be doing something else, not hopping from Mars and Earth and all of its glaciers, something else in academia or outside of it, what would you want to do?
Gosh, well, I really like Mars, so I can't, and Earth, and I can't really imagine doing much else. But I think before I sort of knew that it was possible to do planetary science in the UK, I was kind of gearing up to do something around biogeography or ecology. I found that really interesting. I found palynology, so the study of pollen. I found that really cool. I got a bit of a chance to play around with that at university. I find ecology really fascinating, the way that everything interplays and all the feedbacks between things and how everything is so dependent on everything else. It's so complex and yet so important. And so I think if I hadn't have been doing this, that's probably what I would have pursued.
That sounds really cool. That's one of those nice sciences where you can actually go out and experience it rather than what we do.
Exactly.
And daydreaming about taking a shovel to Mars.
This is why I've come back to Earth for a bit, because I think it is important to ground yourself and to see these things in the field and from remote sensing. So in a way I sort of imagine that I am looking at Mars when I'm looking at landforms. It's handy.
Brilliant. Well, Francis, thank you very much for joining us. That was a fascinating topic of discussion. We'll be sure to link your Twitter in the episode description. But also, if you want some more Earth and planetary science content, we're on social media everywhere, from Facebook to Twitter to Instagram. We're at Earth Solar System. Links will be in the episode description. In the meantime, Francis, thank you very much, and we'll see you all next week.
Cool. Thank you very much.